Lecture 2, Addition. The following is the definition of free abelian group.
While the definition on the preceding page may look complicated, it really isn't. For example, suppose I want to create the finitely generated abelian group generated by a coneflower and a rose. Well, the elements of the group will just be linear combinations of coneflowers and roses. So for example, what does it mean to have 4 coneflowers plus 2 roses? Well, it means that I've got 4 cornflowers and 2 roses. Addition is similarly easy. I can take my 4 cornflowers plus 2 roses and add 3 coneflowers plus 1 rose, and well, what do I now have? I now have 7 coneflowers and 3 roses.
A free abelian group consists of all linear combinations of generators x1 through xk where the coefficients are integers. An integer is just a whole number such as -2, 0, 7, 100, etc. Suppose we have 2 generators x1 and x2. Since our coefficients are integers, the free abelian group will be denoted by z of x1 and x2, where we will use x1 and x2 instead of a rose and a coneflower. Note, we can use any symbols we want, but we will usually stick to letters such as x1 and x2. Thus, z of x1, x2 consists of all linear combinations of x1 and x2 with integer coefficients. Thus, 4x1 plus 2x2 is an element of this group, as is 1x1 minus 2x2. Minus 3x1 is also a linear combination of x1 and x2, but the coefficient in front of x2 is 0. Any linear combination of x1 and x2 is in this group where the coefficients k and n must be integers, i.e. whole numbers. Addition is performed by combining like terms. Whether I'm adding 4 roses and 3 roses, or 4 x1s and 3 x1s, I still get 7 of that object. Thus, 4x1 plus 2x2 plus 3x1 plus x2 gives us 7x1 plus 3x2. In the next example, 2x2 cancels out with minus 2x2, leaving us with 4x1 plus x1, giving us 5x1. In other words, formal sum starts with just counting, where we do addition by combining like terms. But the addition part can be quite useful when describing objects, which we will see in the following slides. We are interested in vertices, edges, and faces. So if I take the free abelian group generated by vertices, edges, and faces, then I can talk about the element 4v plus 5e plus 1f. Note that this one formal sum does not tell us how to draw this complex. There are many different complexes with 4 vertices, 5 edges, and 1 face, but we can still use formal sums to describe a complex. We will first focus on a simpler complex, one with no faces, in other words, a graph. First, we want more objects to count. We will give a different label to each vertex and edge. In the earlier example, we only had 2 objects to count, just v and e. Now we will label each of our vertices individually, so we have v1, v2, v3, and v4, as well as individually labeling our edges, e1, e2, e3, e4, and e5. So each vertex and each edge is given a unique identifier, so we now have 9 objects. We can add together any collection of objects, including those of different dimension, for example, 0-dimensional vertices and 1-dimensional edges. But we will often be interested in sums of the same dimension. So for example, adding up all the vertices, v1 plus v2 plus v3 plus v4, is an example of an element in Z of V1 through V4, while adding up the edges E1 through E5 gives us an element in the free abelian group generated by the edges E1 through E5. A more interesting example is the sum E1 plus E2 plus E3. We can use formal sums to describe our graph. For example, I can note that E1 plus E2 plus E3 is a cycle. I can also note that E3 plus E5 plus E4 is also a cycle. Formal sums give me a language in which I can identify cycles and other interesting features about our graph. But since we are working over the integers, we would like negative numbers to have a geometrical meaning. Note how I am traveling in a different direction along E3 when I describe these two cycles. For the cycle E1 plus E2 plus E3, I travel from the vertex V3 to the vertex V1. While for the cycle E3 plus E5 plus E4, I travel along E3 in the opposite direction. Thus, what we really want to work with is oriented graphs. Here we have an oriented graph, also called a directed graph, where we use arrows to orient the edges. So now the edge E1, for example, the edge E1 points from the vertex V1 to the vertex V2 and is denoted by this arrow. So our objects will be oriented edges, i.e. edges connecting two vertices but with an arrow directing us from one vertex to the other vertex. I still have a free abelian group generated by 5 objects, but now our 5 objects are the oriented edges E1 through E5. If I wish to reverse the orientation of an edge, I just multiply that edge by -1. So multiplying by -1 changes the orientation, changes the direction of my arrow. So now my arrow points in the opposite direction when I multiply by -1. So now negative numbers have a particular meaning, that of reversing orientation. I still have the cycle E1 plus E2 plus E3, but now I can talk about the cycle of minus E3 plus E5 plus E4. So the orientation tells me how to travel along the cycle. So in the first example, I travel in the direction E1, E2, E3, while in the second example, I travel in the direction minus E3 plus E5 plus E4. Note that this makes sense when adding cycles. When I add these two cycles, the edge E3 will cancel out. So when I add the cycle E1 plus E2 plus E3 to the cycle minus E3 plus E5 plus E4, then I get cancellation of the cycle E3, both in the picture because I travel along E3 in both directions, as well as algebraically. So I now have the cycle E1 plus E2 plus E5 plus E4. So when our coefficients are integers, we will work with oriented edges. In the next lecture, we will discuss working with Z mod 2 coefficients, which will greatly simplify calculations and will allow us to ignore orientation. But the next lecture's simplification does come at a cost of losing some information. So for today, we will continue with oriented edges. Abelian in free abelian group means that we can commute objects. So for example, E5 plus E4 is equal to E4 plus E5. I commuted the edges, i.e. I moved the edges E4 and E5 to get E5 plus E4 is the same as E4 plus E5. Thus, if I take the path E1 plus E2 plus E3 plus E1 plus E2 plus E5 plus E4, well, then I get 2E1 plus 2E2 plus E3 plus E4 plus E5. But I can take a different path and get the same sum. For example, I can do E1 plus E2 plus E5 plus E4 plus E1 plus E2 plus E3. And that also gives me the exact same sum. Thus, by allowing commutativity, we do lose information. These two different paths are described by the same sum. But we will see in a later lecture that this method still has a lot of power. Boundaries will be very important in later lectures. The boundary of E1 is V2 minus V1. The minus sign denotes that the edge E1 points from V1 to V2. So this minus sign here denotes that if we've got this edge E1, then V2 minus V1 means that we start at V1 and we end at V2. So our V2 minus V1 means our edge starts at V1 and it ends at V2. We will use shorthand notation to denote boundary. Thus, the boundary of E1 equals to V2 minus V1. We can also calculate the boundary of E2. So our edge E2 starts at V2 and ends at V3. So since it ends at V3, we have that the boundary of E2 is V3 minus its starting vertex of V2. Similarly, the boundary of our edge E3 ends at V1, starts at V3, so it's the ending vertex V1 minus the starting vertex V3. If we add these boundaries together, so add them up here, when we take the sum, everything cancels out. And we just get that the boundary of our cycle is 0. This makes sense since our E1 plus E2 plus E3 is a cycle which does not have any boundary. Thus, the algebra gives us what we expect. The boundary of a cycle is 0. This extremely useful fact will allow us to define simplicial homology, which we will define in a later lecture. In the meantime, let's add a face. But it should be an oriented face. We will use the yellow arrow to denote the orientation of this face. There are two possible orientations, clockwise shown on the left, as well as counterclockwise shown on the right. If we travel in the clockwise direction, the boundary of this face will be E1 plus E2 plus E3. Since our group is abelian, we can also denote this boundary, the cycle, as E3 plus E1 plus E2. So E3 plus E1 plus E2. And since we can commute any two objects, we also have that this is equal to E3 plus E2 plus E1. We now have a simplicial complex. We will more formally define simplicial complex in a later lecture, but I'll define the basic building blocks here. A simplicial complex starts with zero-dimensional vertices. Since a vertex is zero-dimensional, we will call them zero simplices. So a vertex will be called a zero simplex. We also have one-dimensional edges. Being one-dimensional, we will call them one simplices. In the next lecture, we will discuss using Z mod 2 coefficients, which will allow us to ignore orientation, but over the integers, our simplices will be oriented. We will always use pictures or a symbol such as E to denote an edge, but we could also use ordered pairs to denote an edge. So the ordered pair V1, V2 denotes that we've got an edge that points from V1 to V2. So it points from V1 to V2. Since a face is two-dimensional, we call that a two-simplex. Again, we will use pictures or a symbol such as the letter F to denote a face, but we can also use an ordered triple to denote an oriented face. But multiple triples can denote the same oriented face. For example, the oriented face V1, V2, V3 is the same as the oriented face V2, V3, V1, and it's the same as V3, V1, V2. If I wish to reverse the orientation and travel in the counterclockwise direction instead, I can reverse the order of the vertices, and so V3, V2, V1 gives me the face with opposite orientation to that of V1, V2, V3. Two triples correspond to the same orientation if one is an even permutation of the other, but we will ignore such details and focus on pictures and symbols. But ordered tuples can be useful when discussing higher dimensional simplices. For example, a three-simplex can be denoted by using vertices V1 through V4. But a three-simplex is three-dimensional, so we can draw it. I just draw the four vertices, connect every pair of edges, fill in all the faces as well as the interior, and I get a solid three-dimensional tetrahedron. I can't draw the four-dimensional four-simplex, but when working with high-dimensional data, high-dimensional n simplices certainly do exist. Note that the boundary of the two-dimensional face is a one-dimensional cycle. We also have that the boundary of a one-dimensional edge is a zero-dimensional object. It's the difference between two zero-dimensional vertices. So when I take the boundary of an object, I go down by one dimension. So the boundary of this two-dimensional face is a one-dimensional cycle. The boundary of a one-dimensional edge is the difference between two zero-dimensional vertices. A zero-dimensional vertex does not have any boundary.